The recent images acquired by the James Webb Space Telescope have left researchers astounded, unveiling an unforeseen reality about the cosmos. Rather than simply broadening our perception of the universe, these images have revealed a disconcerting truth. Our current understanding is inadequate to grasp the vast possibilities of the universe in its early stages. The present theories regarding the origin of the cosmos are beginning to approach their limitations, prompting the necessity to revisit and explore alternative hypotheses concerning its formation. This situation gives rise to the pivotal question of how the universe developed and why these findings are confounding even the most seasoned experts in space studies. Consequently, there's a pressing need to probe deeper into the actual nature of the Big Bang and the continuously shifting details it presents. It may now be necessary to reassess the Big Bang theory itself, as it has often been misinterpreted in popular discourse. The Big Bang was not just an explosion within an already existing space, but rather it marked the inception of space itself, occurring roughly 13.8 billion years ago, alongside the emergence of matter and time. A fundamental concept in genuine science and cosmology is the notion of a singularity, a location where gravitational forces become so intense that spacetime's curvature becomes infinite. After billions of years since the formation of the universe, we now observe that our cosmic abode exists as part of an expansive and collaborative structure. For researchers, this represents a critical component of the universe's persistence, underlining its continuous expansion. The universe doesn't merely drift into pre-existing space. Instead, space itself keeps growing, as conventional theories have proposed. The first stars are believed to have started radiating light approximately 200 to 300 million years following the Big Bang, marking the conclusion of the so-called Dark Age of the universe. This period was when the first brilliant celestial bodies began to coalesce, eventually forming mature galaxies. However, the rate at which these galaxies developed remains an unresolved puzzle. A significant breakthrough occurred on July 22, when the James Webb Space Telescope revealed its first set of images, showing several galaxies, some of which were already in existence around 300 million years after the birth of the universe. Although these galaxies were far younger than those observed today, they were noticeably smaller and less massive, consistent with the scientific models of that era. In the universe's early stages, the matter density was too low to create galaxies as large as the ones we see today. The discovery started with 6 remarkable redshifted bright spots detected by the James Webb Telescope, setting off one of the most crucial cosmic enigmas of recent times. These newly found galaxies, despite being similar in age to earlier recorded ones, appeared nearly as large as our Milky Way. This revelation has ignited intense interest within the realm of Big Bang cosmology. After examining a sequence of images captured by the telescope's near-infrared camera, scientists confirmed the presence of these distant galaxies, utilizing redshift data to determine that their light had traveled for over 1 billion years before reaching Earth. As a result, these galaxies were already in existence between 570 and 700 million years after the confirmed Big Bang event. This extraordinary finding presents a challenge to traditional cosmological assumptions, which had predicted the formation of much smaller and less developed galaxies during this phase of the universe's history. In contrast, the James Webb Telescope unveiled galaxies nearly as large as the Milky Way, defying previous expectations. The stars bound together by gravity within these galaxies had already amassed mass surpassing 10 billion times that of the Sun. One such galaxy even exhibited indications of a mass greater than 10 billion solar masses. However, whether this hypothesis is completely accurate remains uncertain. Even if this assumption holds, the mass in the early universe would be considerably higher than anticipated, raising further perplexing questions. The galaxy's discovery challenges almost all conventional cosmological theories, and even if one of these galaxies is verified, it would compel us to reconsider our prior beliefs about the formation of these early cosmic structures. The matter density in the early universe would need to be much greater than originally estimated. An alternate explanation could be that these galaxies formed in a way entirely unfamiliar to us. These revelations are prompting scientists to re-examine the Big Bang theory. Many space specialists express frustration over these findings, often voicing their concerns in scientific publications. Those questioning current models are frequently labeled as unorthodox or extreme. Nevertheless, it's clear that even the Staunchest defenders of the Big Bang theory are grappling with unresolved questions. These inquiries involve fundamental issues, such as how, 13.8 billion years ago, something could emerge from nothing. Could something genuinely emerge from nothing? Or was there a catalyst for this event? Or did it occur randomly? Stephen Hawking famously argued that the nature of time, as we understand it today, began with the Big Bang. This suggests that the process could not have been initiated by any external force or triggered by another event. Similar uncertainties exist regarding the uniformity of radiation and matter across the universe. No matter where we look or at what distance, we observe a comparable distribution of systems, nebulae, and radiation across the cosmos. Contemporary scholars explain this phenomenon using the theory of cosmic inflation, though other researchers have expanded upon this idea, suggesting that the universe has expanded in a more chaotic manner. According to this perspective, expansion occurred only in specific areas like bubbles, while other regions continued to grow without end. This model introduces the intriguing possibility that other universes might exist within these expanding bubbles, each governed by its own set of physical laws. This viewpoint implies that our universe might not be the entirety of existence, but rather just a fragment of a far more intricate and expansive structure. Within this framework, the concept of an eternal cycle of breakdown and rebirth for the universe is presented. However, this is not the only cosmological perspective. For example, an article published in NASA's Big Time magazine in 1955 proposed that the universe may never have had a Big Bang and that it has existed infinitely, possibly for an eternal duration. In this interpretation, the expansion of the universe would be non-existent, with matter evolving gradually over time, creating the impression of a slow, continual development. One of the more fascinating hypotheses emerges from quantum physics and string theory. Some studies have hinted that our universe, and everything within it, could be a projection or simulation originating from a higher dimensional reality. While this might seem like the premise of a science fiction narrative, it shares connections with the Kardashev scale, which measures a civilization's energy usage by its ability to harness the power of an entire galaxy. If a Type 3 civilization existed, capable of utilizing all of a galaxy's energy, it might have created an ideal simulation of a universe. However, validating this scenario presents considerable challenges. Delving into the depths of cosmology and the origins of the universe leads us into a realm of profound mystery and continuous scientific exploration. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of existence, testing established models and prompting scientists to rethink fundamental aspects of our understanding of the universe. At the core of these debates lies the theory of the universe's origin, which forms the foundation of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from a hot and dense state, expanding rapidly and giving rise to the space-time and matter we observe today. This monumental event wasn't just an explosion within pre-existing space. It also signified the birth of space itself. The idea of a singularity, where gravitational forces become so immense that spacetime's curvature becomes infinite, supports our understanding of this early phase of the universe. However, the discovery of large, mature galaxies only a few hundred million years after the Big Bang challenges the conventional ideas about the rapidity with which the first structures formed. These findings suggest that the early universe had a far higher density of matter than previously believed, prompting questions about how such substantial structures could have developed so quickly. This compels cosmologists to reconsider how galaxies like those observed by the James Webb Space Telescope came into being so soon after the universe's birth. One key theory arising from these discoveries is cosmic inflation, which posits that the universe expanded exponentially during the first moments following the Big Bang. This rapid inflation is thought to explain the uniformity of the cosmic microwave background radiation that we observe today. However, recent findings are introducing complications into our understanding of the early universe's development, suggesting that inflationary models might need to be adjusted. The formation of these early massive galaxies raises vital questions about the roles of dark matter and dark energy, two mysterious substances that make up most of the universe's mass and energy. While dark matter is believed to provide the gravitational framework needed for galaxies to form, scientists still lack a clear understanding of its distribution and characteristics in the early universe. In response to these unresolved challenges, theoretical physicists are investigating alternative cosmological models that contest the standard Big Bang theory. Some of these ideas propose that our universe may be just one of many within a vast multiverse, each governed by its own unique set of physical laws. These concepts, emerging from string theory and quantum cosmology, present a far more complex and interconnected cosmos than previously conceived. One such hypothesis gaining popularity is that of timeless inflation, in which universes are perpetually created within a larger expanding space, suggesting that our universe could be one among an infinite number of others, each with distinct physical characteristics. The challenge, however, lies in acquiring observational evidence to support these speculative theories, as they extend the limits of what can be tested through scientific means. Another provocative concept proposes that our universe might exist within a computer-generated simulation, drawing comparisons to advancements in artificial intelligence and computational science, where simulations can recreate intricate systems. If this idea proves true, it would fundamentally alter our perception of reality and provoke substantial philosophical and scientific questions regarding the nature of existence itself. As observational astronomy advances, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to unveil even more of the universe's secrets. Future observations may provide deeper insights into the cosmos's earliest moments, potentially offering clues about its ultimate destiny and the core principles that govern its ongoing evolution. Meanwhile, particle physicists remain dedicated to unraveling the fundamental particles and forces that shape the universe. The pursuit of unifying gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central objective in theoretical physics. In the field of quantum mechanics, debates continue about the nature of time itself, with some theories suggesting that time itself could evolve or even behave differently at the most fundamental levels. Grasping the true nature of time within the context of cosmology could revolutionize our understanding of the universe's origins and development. Furthermore, the search for extraterrestrial life continues to captivate both public curiosity and scientific research. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our knowledge of planetary diversity and the potential for habitable environments beyond Earth. Future missions, such as the James Webb Space Telescope's analysis of exoplanet atmospheres, could uncover biosignatures pointing to life beyond our planet. As scientific exploration advances, philosophical inquiries into humanity's place in the universe intensify. The pursuit of answers to questions about existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration will remain central to discussions across both scientific and philosophical fields. As scientific progress continues, the questions surrounding the origins and nature of the universe become more pressing. The discoveries made by the James Webb Space Telescope have highlighted the need for new approaches in understanding the cosmos. While traditional models of the universe's formation have been foundational to cosmology, recent findings have challenged these ideas and opened the door for new paradigms. These revelations suggest that our perception of the universe's history and structure may need to undergo a fundamental shift, one that embraces the complexity and uncertainty inherent in the cosmos. Cosmologists are now faced with the task of revisiting their assumptions about the Big Bang and its aftermath. The idea that the universe began as a singular, explosive event in a point of infinite density is still widely accepted, but the new data raises serious doubts about the accuracy and completeness of this model. The discovery of massive galaxies in the early stages of the universe suggests that the process of galaxy formation may have been much faster and more efficient than previously thought. This has led to a reevaluation of how galaxies form and evolve, with scientists proposing new mechanisms that could explain the rapid growth of early cosmic structures. One such hypothesis involves the idea of dark matter and dark energy playing a more prominent role in the formation of galaxies than was originally believed. Dark matter, which is thought to exert a gravitational influence on visible matter, could have played a crucial role in shaping the structure of early galaxies. However, the exact properties of dark matter remain elusive, and its behavior in the early universe is still poorly understood. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, may have contributed to the rapid development of galaxies and other cosmic structures. Another area of inquiry is the role of cosmic inflation in shaping the universe's large-scale structure. The theory of cosmic inflation suggests that the universe expanded exponentially in the first moments following the Big Bang, leading to the uniformity we observe in the cosmic microwave background radiation. However, recent observations, including those made by the James Webb Space Telescope, have raised questions about the validity of this theory. Some scientists now believe that inflation may not have been a smooth, uniform process and that local fluctuations could have influenced the formation of galaxies and other structures in the early universe. These emerging questions point to the necessity of a more nuanced understanding of the universe's origins. While traditional models like the Big Bang theory have provided a solid foundation for cosmology, the new data is forcing scientists to reconsider many of their long-held beliefs. This is not an easy task, as the implications of these discoveries challenge some of the most fundamental principles of physics. Nevertheless, the pursuit of answers to these questions is essential for advancing our understanding of the cosmos. In addition to revisiting established cosmological models, these discoveries are also prompting new avenues of research into the fundamental nature of space and time. The concept of space-time, which has been a cornerstone of our understanding of gravity and the behavior of matter, is now being examined more critically in light of the new data. The idea that space-time itself may be more dynamic and flexible than previously thought is gaining traction, with some theories suggesting that space-time could be subject to changes that are not yet fully understood. As scientists continue to probe the mysteries of the early universe, they are also looking to other fields of study for insights. Quantum mechanics, which governs the behavior of particles on the smallest scales, may hold the key to understanding the fundamental forces that shaped the universe's formation. The relationship between quantum physics and general relativity, the theory of gravity developed by Einstein, is one of the biggest unsolved problems in modern physics. New discoveries in quantum mechanics may offer solutions to some of the questions raised by the James Webb Space Telescope's findings. One particularly intriguing idea comes from the field of string theory, which suggests that the fundamental building blocks of the universe are not particles, but rather tiny vibrating strings of energy. According to string theory, the properties of matter and the forces that govern the universe arise from the way these strings vibrate. If string theory is correct, it could provide a unified framework that explains both quantum mechanics and general relativity, offering a comprehensive understanding of the universe's origins. At the same time, advancements in particle physics may help scientists unravel some of the universe's deepest mysteries. The discovery of new particles, such as the Higgs boson, has already provided important insights into the fundamental forces that govern the universe. Further research into the behavior of subatomic particles could reveal more about the nature of dark matter and dark energy, two components that remain largely mysterious.